Is life an exclusive phenomenon on our planet? Could life exist elsewhere? Humanity has always asked itself this question, and no answer has been found so far. Despite this, thanks to recent advances in astronomy, we're closer to solving this mystery. Our solar system is home to many planets and moons explored by space probes, while sophisticated telescopes search for answers in the universe. These studies provide impressive results. In the last 2 decades, astronomy has made significant strides in showing that most stars contain planets all over the place, and more planets than stars. NASA's Kepler space probe made these discoveries possible. Its launch in 2009 marked a milestone in the search for life beyond the solar system. Our galaxy alone has billions of exoplanets like Earth. It is hard to imagine that anywhere in the vastness of the universe there are no planets like Earth that can harbour life. The universe contains more than 100 billion galaxies. Finding them is only a matter of time. It is a game changer, and it challenges the notion that life might be possible somewhere else. 2 game-changing discoveries, exoplanets and extremophiles. This leads us to think that life has existed in our solar system, or has perhaps existed in harsh environments in the past. Perhaps there is life in the strange methane lakes of Titan. There might be life beneath the mysterious ice of Europa's oceans. There might be life beneath the gigantic geysers of Enceladus, perhaps on Mars's desert plains. There must have been a second Genesis within the same solar system. Life's origins are likely to occur within the same solar system. It is unknown if life will be discovered on one of these moons or planets in our solar system. The same applies to exoplanets. Life in outer space is one of nature's greatest mysteries, and we are closer than ever to solving it. It requires an incredible combination of ingredients to produce living matter. It may be the greatest mystery in nature. Materials exhibit specific properties, such as responsiveness, growth, metabolism, and energy transformation. There is no consensus regarding what life is, and we do not yet have a working definition. Maybe my favorite definition would be that life is some chemical entity that is self-contained and capable of Darwinian evolution through natural selection. According to some studies, life may have begun on Earth as early as 4.1 billion years ago. Our planet is only slightly older than that. This raises an interesting question. Do we need a planet like Earth to sustain life? The answer to this question is complex. There was a time during the universe's history when it was only 10 to 17 million years old, when the chemistry of life began shortly after the Big Bang, 13.8 billion years ago. There is a possibility that life emerged independently at many places in the universe. Another possibility is that life originated less frequently, then spread via meteoroids or comets between habitable planets, a process known as Panspermia. There is a possibility that organic molecules formed within the photoplanetary disk of dust grains surrounding the Sun before Earth formed. This process may occur on other planets and moons of the solar system besides Earth. There are also planets around other stars known as exoplanets. Humanity has wondered if we are alone in the universe, and if life has existed beyond Earth throughout history. Those questions may take a long time to answer. We have, however, always been intrigued by them. For a very long time, scientists have been interested in the question of life beyond Earth. It can be traced back to ancient Greek, Roman, and Chinese writings, a belief that life exists beyond Earth. When searching for life in outer space, a primary concern is establishing the conditions in which endothermic or energy-absorbing reactions occur. Organic molecules are built from carbon-based raw materials. The next step is to find if there is life on other planets. We are looking for the building blocks of life on Earth, and we know there are carbon, hydrogen, oxygen, nitrogen, and others. In our understanding of life, these basic building blocks are ubiquitous. For biochemical reactions to occur swiftly and steadily, a liquid or dense gas is necessary as the solvent. For liquid water to support life on Earth requires specific atmospheric composition and temperatures. It is essential to have 3 things for a habitable environment: liquid water, organic material, and energy. Additionally, several locations contain all 3 things in the solar system. Life can only exist if the critical conditions are met. Immediately the question arises, how many planets and moons in our solar system meet these requirements? Our solar system has 3 potential candidates with liquid water on its surfaces, considering that liquid water is vital for life on other planets. Mars is the most likely candidate. Europa the moon of Jupiter, and Enceladus the moon of Saturn. There is another candidate for supporting life in our solar system besides Mars, Europa and Enceladus, which may have liquid water on their surfaces. Titan, Saturn's largest moon. Titan was a great mystery to astronomers until 2004 because an opaque haze obscured its surface. When Cassini reached Titan, the probe Huygens was released. Suddenly, everything changed. As the Huygens camera descended through the haze, these are the images that it captured. Titan has a similar landscape to Earth's, with mountains, valleys, and plains. The probe discovered something unexpected when it touched the surface. Pebbles were scattered everywhere. They looked like riverbed rocks on Earth. You can see that the pebbles have been rounded, and rounded by rivers and torrents. We understand they are water ice, which behaves like a rock because of its hardness. What caused these rocks to erode? Does water exist on Titan's surface? Titan is covered with hundreds of lakes, as Cassini's radar revealed. Water should be solid at a temperature of minus 180 degrees Celsius. There is one big difference, however. Ethane and methane are the principal ingredients. They do not contain liquid water. Titan's cold temperature turns these two hydrocarbons into liquids, but they are volatile gases on Earth. As Titan's atmosphere contains methane and ethane, among other organic materials, its chemistry is very different. But it is reminiscent of what Earth may have been like before life was abundant on Earth. We expose some of these worlds to high levels of radiation because their atmospheres are very thin, which is very far from the heat of the sun. Because of this, their environments are hostile. Perhaps, however, there is life in some of these worlds. Also newly discovered are extremophiles, organisms that live in environmental conditions that I was told could not support life when I was a student. The temperature is too high. The temperature is too cold. The acidity is too high. The pressure and radiation are too high. These conditions have allowed them to thrive. Therefore, they are flourishing. Extremophiles are a game-changing new field of study. This changes our perspective on life outside our planet. Bacteria that exist on Earth in high temperature, toxic hydrothermal volcanic vents, and those that live in extreme hostile environments on other planets, including freezing temperatures and little sun exposure, are extremophiles that provide insight into the potential for life to have developed in such hostile environments. The solar system exploded in response to this new understanding of what was necessary for life to survive. Our understanding of habitability and habitable environments grew in ways we never imagined. It is now much more likely to discover life on any of these distant worlds in our solar system. Eventually, we will find it. We have 160 planets and moons in the solar system. So far, the attention of astrobiologists have been focused on Mars. There are many indications that Mars has extensive areas of liquid water in its ancient history, similar to Earth. It had a thick atmosphere. There were abundant sources of energy for life. Furthermore, there was a good supply of organic molecules. Mars does not need words to describe it when comparing the two planets. There are mountains, there are canyons. There are polar caps, there are dunes. A warmer and wetter Mars may have existed in the past, evidenced by dried-up riverbeds and vast canyons blasted out by epic floods. Raging rivers may have carved valleys on Mars. A polar ice cap may have existed. In the presence of water, we have found volcanoes and minerals. At least 4 billion years ago, there was much evidence of liquid water during Earth's history. There may also have been transient water. As Mars cooled down and lost its atmosphere, all that water vanished from the surface. Was life ever able to establish itself on Mars? Some people think we already had evidence of ancient life on Mars, as we search for evidence for ancient life on Mars. The Allen Hill meteorites are an excellent example of that. Previously, we had a Mars piece in the lab. Currently, it is in storage. Allen Hill's 84001, a rock that landed on Earth on the Antarctic ice sheets after being blown off Mars millions of years ago. We realized by the gases in that rock that it is a piece of Mars as the ice melts, and those black rocks are picked up in the melt pools. It was then dissected at microscopic scales. Additionally, we had a significant scientific controversy in that scientists claimed certain features in that rock could only be explained by biology, while others argued the contrary. Geology can explain the features of that rock. There has been a search for life on Mars for decades. First attempts at finding microbial life on the red planet were made in 1976. In 1997, the Pathfinder mission took an additional step in seeking life adventure, 2 decades after the original one. The team found magnesium, aluminium, iron, and phosphate in Martian rocks, all of which support life. Phoenix explored the North Pole of Mars in 2008. A white material was found after digging a few inches that had evaporated several days later. Water ice was determined to be the material. Observations by satellites found plenty of water under a layer of frozen carbon dioxide on both polar caps. If all that ice ever melted, the world would be covered with a sea over 80 feet deep. A similar satellite also found that ice was buried beneath the desert plains all over. It was an astonishing finding. The Martian surface is blanketed in water ice, but could life exist within the ice itself? In dry valleys in the Antarctic, where conditions are like those in the Antarctic, it has been discovered that extremophile microbes can survive. Mars is currently dry and freezing. In some ways, it is like the Antarctic today, and in other ways, it is like a frozen desert. If you opened a container of liquid water, it would not be stable. The ice would evaporate instantly because of its dry nature. They found the ice buried under a layer of dry dirt. When dirt meets ice on Mars, a thin liquid film is formed where extremophiles can survive for just a short period. They flourish only for a few warm weeks during the summer because they remain frozen and dormant for most of the year. Some microorganisms still exist today that involve thin films of water, or perhaps more liquid water, because the deeper you go, the more chances you have of finding liquid water. Mars's summers are often hot and dry at the equator, so the buried ice might melt and create conditions like those in the Antarctic dry valleys. In the rocks or under rock coatings are probably any microbes that may have been present. Therefore, we have been looking at microbes living below Mars's surface as an analogue site, because it might also apply to Mars. Mars may also possess liquid subsurface water. The Olympus Mons volcano on Mars contributes internal heat that sustains subsurface water. If Mars has hydrothermal vents, it might also be possible that there are extremophiles like those present in terrestrial hydrothermal vents on Mars. This is, however, unlikely to be the case. Having liquid water on the surface would cause everything to change. If this hypothesis is true, a future mission could prove it. NASA's Mars Reconnaissance Orbiter made a massive discovery in September 2015. On Mars today, liquid water flows intermittently, as observed by this spacecraft. Researchers detected hydrated minerals on slopes near mysterious streaks seen on Mars through an imaging spectrometer. In warm seasons, they darken and seem to float down steep slopes. In cooler seasons, they fade. The discovery confirmed what anyone could have imagined about Mars's current surface. Water is present. Since the pressure at the surface of Mars is so slight, it can only remain stable for a short time, as it is not pure, transparent water. Instead, it is very fresh, very salty water. The ephemeral streams of liquid water might have produced microbial life. Our hypothesis will need to be confirmed by future rovers and explorers. The Mars exploration missions of NASA and the European Space Agency, both part of the Mars exploration program, will lead to new insights into Mars. Space missions to Mars have been primarily focused on following the water on the planet since 2007. Both ice and liquid water have been detected, aiming foremost to explore its habitability. During our ongoing exploration of Mars, we find more and more evidence that ancient Mars was unquestionably a place for life. So the question is, how did life emerge on Mars? In this case, how did it develop? And what clues remain today, since it happened so long ago? Missions to Mars are ultimately aimed at preparing human exploration, a milestone for humanity. European Space Agency and Roscosmos, with NASA's participation, announced the ExoMars program as the first step in this ambitious exploration program. The mission's primary aim will be to search for biosignatures left behind on Mars. The ExoMars program comprises multiple missions. During ExoMars 2016, the first mission will be the Trace Gas Orbiter. Using this orbiter, the goal is to search for methane and other gases connected with biological processes on Mars. 2018 ExoMars rover and landing platform is the second mission of the ExoMars program. In order to sample various depths beneath the surface and find liquid water, the ExoMars rover will use a 2-meter core drill. Initially, the drill was to penetrate a few meters into the sediment. The drill could then find evidence of salt. NASA's Mission Mars 2020 is the third step in this exciting Mars exploration program. During Mars 2020, the rover will look for ancient microbial life on the surface of Mars and study various rocks and soils. The Mars Global Surveyor's primary task is to observe weather and dust in the Martian atmosphere and test how well it can extract oxygen from the planet's carbon dioxide atmosphere. Human exploration will take place shortly after the Mars Global Surveyor is launched. One or more of these missions might solve the enigma of whether life existed on Mars in the past or present. Another more distant world may host life. One of the fascinating Jovian moons, Europa, is our next stop searching for life. The moon is the largest of Jupiter's 4 moons. Despite its small size, its surface is icy, and its temperature is minus 160 degrees Celsius. Our knowledge of Europa comes from NASA's unmanned space probe Galileo, which flew by Europa 12 times. These were the probe's first images of Europa. There is a smooth layer of water ice covering it. The surface is one of the smoothest ever seen on a solid object in the solar system. Europa has a unique surface in the solar system, with very few craters, showing that its surface is constantly being reprocessed. A similar climate to that of sea ice exists on Earth. A few ice blocks are visible on its surface, but they seem to fit together like a puzzle. These icebergs may have been shifted under slushy water or liquid. Some of these cracks may extend down to the ocean or at some point to allow some water to circulate. That Galileo could detect all those things together contributes to our understanding that Europa has a liquid ocean beneath its surface. Galileo detected a magnetic field in 1996, showing that the planet must have an ocean salty enough to conduct electrical current. This ocean may be as deep as 60 miles. There seems to be a pretty clear correlation between the studies and measurements made in the past decades and an ocean under the ice. Here we have the first element needed to sustain life: liquid water. If water temperature falls below 160 degrees Celsius, can it remain liquid? Jupiter has the key to melting the icy crust because of mysterious internal heat. We have proposed that Europa's centric orbit around Jupiter may cause tidal heating. The tug-of-war between Jupiter and Europa is caused by gravitational pull. Despite its apparent seal, the ice and surface of Europa are cracking. It makes sense that all this friction creates lots of energy and heat, and we have good reasons to believe that the water is being heated by hydrothermal action. Deep within volcanoes, hydrothermal vents may provide energy for heating and maintaining liquid water. Our planet has 2 of the 3 necessary conditions for life: liquid water and an energy source that comes from inside its surface. Organic compounds would be the last thing we would need. The chances of life flourishing would skyrocket. As Jupiter's radiation impresses this carbon dioxide onto Europa's ice, Galileo observed it contains carbon dioxide. Its products are simple organic molecules like formaldehyde, steps towards life. Tidal action could also mix life-sustaining substances in the ocean, as mentioned previously in Europa. It is yet unknown whether this occurs. NASA reported a discovery on the icy crust of Europa in 2013. Some materials similar to clay were detected, specifically phyllosilicate. Clay is a mineral that forms in many waters on Earth, and clays are minerals that come from phyllosilicates, which are layered silicates. Clays are believed to have been some of the original minerals present when life developed. It is hypothesized that organic associated minerals collide with an asteroid or comet. In Europa, life could exist in places never imagined because it would have liquid water, an energy source, and chemical building blocks derived from comets and asteroids. Within the Arctic ice sheets 12,000 feet beneath the surface, hydrothermal vents are spewing out superheated water with many toxic chemicals. Researchers believe similar vents may also exist on Europa's ocean floor. This may be one of the ocean's energy sources. Europa will be mainly volcanic. Several miles of the Arctic seafloor is covered with extremophile microorganisms clustered around vents. These discoveries show that there may be life on the European continent, perhaps the best candidate to search for life in Europa. There are now challenges to prove that life has thrived in such a bizarre environment. European Space Agency and NASA plan to send 2 missions to the continent to explore its habitability in the next few years. A new NASA mission to Europa was approved in 2015 to investigate its environment and see if it's habitable. In the 2020s, NASA will launch a spacecraft to perform multiple flybys of Europa. The probe will be radiation tolerant and highly capable during repeated close flybys of the icy moon. Additionally, we will use radar and magnetic field detectors and other equipment to look under the surface of the ice shell to learn more about its structure and the structure underneath the shell. The European Space Agency is developing a parallel mission. Jupiter Icy Moon Explorer, the so-called JUICE mission, is scheduled to launch in 2023 and arrive at Jupiter in 2030. Europa and two of Jupiter's largest moons, Ganymede and Callisto, will observe this spacecraft for at least 3 years. It will take a decade for us to determine whether Europa contains life. Europa is not the only wonder of the solar system this far out. There are 60 moons on the planet, but only one small mysterious one. Enceladus is a tiny, icy moon, only 300 miles across. This tiny moon has become exobiology's primary target during the last few years, because its unusual conditions for harboring life have been revealed. Is it possible for similar conditions to exist on other moons orbiting planets farther from the Sun orbiting Saturn? We know most about Enceladus thanks to Cassini's mission, operating for many years. Currently, an orbiter is studying the Saturn system and its moons, but Enceladus is one of particular interest. We could see this little world up close for the first time thanks to Cassini. Here are the first images Cassini took. There are fissures, crests, and cracks on the white, shimmering surface of the South Pole. Cassini made an unexpected discovery. The spacecraft found some strange cracks in blue. There were 4 parallel fissures. These were dubbed tiger strips. The fissures were 75 miles long and hundreds of feet deep. This is like fault lines on Earth. The thermal radar on Cassini revealed an unexpected finding after several flybys. As they were in the South Pole, the tiger stripes should be colder than the rest of the moon. Instead, they were radiating heat. At minus 80 degrees Celsius, the fissures were over 120 degrees warmer than the rest of the moon. In this area, we observe evidence that something profound is taking place in the potential for a habitable environment. What was more surprising was that it had not been discovered yet. Cassini captured an astonishing image after it was reorientated. Massive jets of ice erupted into space. Cameras captured plumes of water vapor and ice crystals emanating from Enceladus's South Pole. Observations of the plumes showed that ice particles were emitted from the tiger stripes hundreds of miles away. The materials are being ejected through fractures on the moon's surface, which appear to connect the surface to the interior. These water jets erupted from their icy surface like geological hotspots on Earth. However, scientists believe Enceladus may also have a source of energy within. It is incredible how such a small moon can generate so much heat to sustain such geothermal activity. In the same way Europa melts ice when it orbits Saturn, friction from the gravitational process causes the moon to heat. This detector analyzed particles chemically and found that some particles are salty, and salt can only be incorporated into particles by evaporating directly off of liquid. That these plumes are coming from liquid under the surface of Enceladus is just another hint. Was there a subsurface ocean under Enceladus's icy crust, similar to that under Europa? We needed more evidence. Next, Cassini analyzed its trajectory before flying past Enceladus to determine how Enceladus's gravity affected the spacecraft. That analysis revealed a density anomaly under the entire South Pole, showing that the plumes originate from a regional sea of water. Depending on where the moon's ocean meets its underlying rock, these jets could result from active hydrothermal vents, prime habitat for life. Despite that, there was no way to prove that life existed beneath the icy crust. Spectrometers on the probes detected something fascinating, and they found the chemical building blocks of life in the jets. The intriguing thing about Enceladus is that it appears to contain the 3 essential ingredients for life: liquid water, nutrients, and organics. Can life exist in this strange and alien world? Using geysers, we could sample the moon's subsurface ocean, and if there is microbial life in the sea, we could find evidence of their existence by examining ice particles from the sea. There will be 2 NASA missions to Enceladus shortly, looking for life on the tiny, icy moon. The first one concerns the journey to Enceladus and Titan's mission, taking a closer look at Enceladus and Titan. This is an astrobiology mission concept to evaluate their habitability. Enceladus's life investigation is the second mission awaiting funding approval. Saturn's moon, Enceladus, would be sampled for ice particles and returned to Earth to study life signs such as biomolecules. Technologically speaking, it would be relatively simple for an orbiter to be sent to Enceladus to capture and analyze the plume's icy particles or bring them back to Earth for further study in the laboratory. However, because of the lack of approval for these missions, we will still have to wait to discover life on this tiny, enchanting moon of Saturn. There is one last great candidate for life close to Enceladus in the solar system. Saturn's largest moon, Titan, has a thick atmosphere and is one of the largest moons in the solar system. It is also the only moon with an atmosphere known to exist. Hydrocarbon lakes were detected by the Cassini-Huygens mission, which flew by Titan in 2004. This world holds many secrets. In a sense, it is the strangest place in the solar system because, aside from the Earth, it is the only place we know of that has liquid seas. However, there is no liquid water on the planet. There are many lakes and seas in this region. Methane and ethane are much less dense than water, so there are no waves in the liquid. They are both volatile gases on Earth. Titan has a temperature of minus 180 degrees Celsius, which means liquid. The landscape of Titan is remarkably similar to Earth. As on Earth, Titan has seas, lakes, smoothed rocks along rivers, mountains, valleys, and canyons. But those mountains and pebbles do not comprise any rock, but of ice so frozen that because of its minus 188 degrees Celsius temperature, Titan's frozen surface behaves like a rock. Cessna's radar images showed liquid methane forming clouds, thunderstorms, and even rain on Titan. On Titan, methane plays a very similar role to the water in the atmosphere. It falls as rain or mist. There are channels and rivers where methane flows, similar to water formation on Earth's surface. As well as organic molecules like methane, ethane, and hydrocarbons, Titan's atmosphere contains conditions that resemble those of early Earth 4 billion years ago that enabled life to develop. There is a similar cycle between liquid methane and Earth's water cycle. Is it possible to act like water on Earth to allow organic molecules to dissolve and interact as a liquid? The answer to that is a complex one. The atmosphere of Titan resembles the atmosphere of a young Earth kept in the refrigerator. Although prebiotic chemistry is very different, the same processes are present. We do not know if the prebiotic processes transform into something biological at Titan's surface or below its surface. As liquid methane and ethane are extremely cold, it would take thousands of years to undergo biochemical reactions. Because freezing temperatures of minus 178 degrees Celsius render these compounds far less effective as solvents, and therefore life-promoting water is more challenging to create. The presence of an atmosphere similar to that of Titan, along with UV radiation, has been shown to generate complex molecules and polymer substances like tholins, which are considered a precursor to life. In reality, chemistry, physics, biology could be people seeking to think in terms of what could be a biology-based method. Such an approach is not optimal for determining the structure of biochemistry. We conclude that Titan has a methane cycle comparable to Earth's water cycle in its atmosphere and geology. There may be life on Titan. There have been many attempts by NASA and the European Space Agency to develop a crewless space mission that can solve Titan's mysteries, but none has yet been approved. NASA's Titan submarine is one of the most exciting missions proposed to learn more about Titan's methane and ethane lakes. Submarines such as this could explore the Kraken Mar, the most significant known liquid on Earth. The mission would have measured organic components on Titan and possibly observed its shoreline. It would have been a first for nautical exploration of an extraterrestrial sea. Like the other proposed mission to Titan, the Titan submarine mission has yet to be approved. Titan can be explored in many different ways, but NASA has not selected them. As a result, no future space missions to Titan have been confirmed to date. However, everything could change if a shocking discovery is made soon. Although it is unknown whether any of these missions will detect life on Mars, Europa, Enceladus, or Titan, what we do know is that we are much closer than ever to answering the question of whether life exists beyond Earth. In 1950, robotic exploration of our solar system was beginning. First, close-up images of Mars were sent by Mariner 4 probe in July 1965. As seen in the blurred images, Mars was devoid of vegetation and had very few canals crisscrossing it as imagined by earlier generations of astronomers. Mars was most widely regarded as a red and dead planet with no chance for life. Since 1965, the world has undergone a dramatic change, thanks to the extraordinary advancements of technology that have allowed us to explore our neighbours in the solar system with more sophisticated space probes. We cannot live without energy, liquids, and chemical building blocks. As a result, life exists beyond Earth in our solar system. A discovery of such magnitude would not only shock humanity, even if it were just microbial life, but allow us to think that we may not be the only ones in the universe. It is possible that such conditions could also exist in outer space beyond the boundaries of our solar system. There is also the new era of space telescopes for exploration, with the James Webb Space Telescope expected to find Planet 9 in the outer skirts of our solar system. NASA's James Webb Space Telescope will become the most powerful telescope in space. With its James Webb Space Telescope launch, what will its images be like compared to Hubble's? In April 1990, the Hubble Space Telescope was launched into low Earth orbit. Its stunning images have captured our attention all these years, allowing us to gain a better understanding of the cosmos. We saw stars and galaxies as we had never seen before in the abyss that had once been a faint and mysterious void. It will be a bit different with the James Webb Space Telescope, scheduled for launch in 2021. NASA notes Webb will observe objects 10 to 100 times fainter than Hubble, thanks to its giant gold mirror and infrared observation tools. What difference will Webb's view make compared to Hubble's? Webb is often described as Hubble's successor or replacement. Although Hubble's science instruments have encountered a few glitches over the years, they are still operating and set to observe in space together, though some distance apart. The high Earth orbit of Hubble is pretty close to us, but Webb will travel out much farther to L2, the Sun-Earth Lagrange point 2, 1.5 million kilometers, that is gravitationally stable. Furthermore, although both Hubble and Webb are large space telescopes, Webb being considerably more prominent, they see the universe very differently. In May, during a news conference, Klaus Pontoppidan, Webb project scientist at the Space Telescope Science Institute in Baltimore, said the telescope would take excellent images. While Webb's images will be better in many ways, they will also be fundamentally different because of the wavelengths. In contrast to Hubble, Webb is designed to detect primarily infrared light. Webb will capture unique images by observing in infrared. You may notice some dust and gas features becoming wispy as you edge into the infrared spectrum, but that is not necessarily a bad thing. According to the fact sheet, Webb will see the light between 600 nanometers nm and 28 microns, while Hubble sees the light whose wavelength ranges from about 700 to 400 nm. Despite Webb observing primarily infrared light, it can still see light red or orange. Mirrors with gold coatings absorb blue light from the visible spectrum but reflect yellow and red visible light that can be detected. Hubble can also observe some infrared wavelengths, so this type of observation is not a complete departure from the way the telescope typically observes. To commemorate Hubble's 22nd anniversary, the Space Telescope captured an infrared image of the Horsehead Nebula in 2013. Despite having a similar sharpness to Webb, Hubble has provided stunning images to the world for decades. The fact sheet states that Webb's angular resolution, or sharpness of vision, will be the same as Hubble's. Compared to Hubble's images, Webb's images are just as sharp. Using Webb's high resolution, NASA says it would see an object 24 miles, 400 kilometers away in detail. However, the Webb telescope has a much larger mirror, 21.3 feet, 6.5 meters wide, than Hubble's 7.8 feet, 2.4 meters, advanced detectors, and is designed to see deeper into the infrared spectrum. NASA explains that Webb will allow scientists to see much farther into the universe by observing infrared light. As a result of its more oversized mirror, the scope can also collect more light to peer even farther into space, which provides scientists with a way to view the universe billions of years into the past. The Webb Space Telescope was designed to observe the first stars and galaxies to form in the early universe. The telescope can see objects 10 billion times fainter than the faintest stars visible without a telescope, or 10 to 100 times fainter than the faintest stars Hubble can observe. In order to make its observations, Webb is equipped with 4 scientific instruments. There are 2 near-infrared cameras, a near-infrared spectrograph, a mid-infrared instrument, an exemplary guidance sensor near-infrared imager, and a slitless spectrograph. These tools will enable Webb to perform imaging spectroscopy, Pontoppidan explained, which is the capture of not only an image but a spectrum of wavelengths for every pixel of the image. There is information on the spectrum of wavelengths present in each pixel in imaging spectroscopy. Scientists can use this information to determine what elements or chemicals might have created the spectrum. Its special imaging tools will enable Webb to do all sorts of other scientific work, such as observing exoplanets transiting in front of stars or analysing a cloud in a star-forming region. Webb pointed to studies that may examine the contents of the atmospheres of exoplanets. NASA, the European Space Agency, and the Canadian Space Agency are all involved in the James Webb Space Telescope. Webb was finally launched in December 2021 atop an Ariane 5 rocket from Kourou, French Guiana, despite another delay. Astronomers may study Planet 9 with NASA's James Webb Space Telescope. Indeed, NASA's James Webb Space Telescope, JWST, one of the most anticipated and talked about pieces of space hardware ever designed, will make observations of the ends of the universe that will likely shake the foundations of cosmology. In addition, it may be able to locate the large super-Earth dubbed Planet 9, which some astronomers believe can be found at 900 AU, or Earth-Sun distances, from our solar system. Like Earth, Planet 9 is expected to be fairly large and far away, so most ground-based telescopes will not be able to detect it, said Stephanie Millam, Deputy Project Scientist for Planetary Science at NASA Goddard Space Flight Center. JWST is capable of fully characterizing the planet, if it is discovered. In the tenuous atmosphere of the putative planet, chemicals such as carbon dioxide will be detected, Millam said. Our solar system will be observed by the JWST starting from the orbit of Mars. As part of its $8.8 billion mission, JWST will also be able to capture some previously unattainable images of Mars and other familiar objects in our solar system, thus closing a gap in solar system science. JWST will continue to provide near-infrared observations for about 6 months after launch. The observatory's primary focus will be monitoring the atmospheres and geology of familiar solar system planets and moons, using methods not possible from the ground or with existing or near-term space missions. During JWST's 1 million-mile orbit, its primary mirror will be 6.5 meters wide, and its sunshade and 4 instruments will offer better sensitivity, spectral resolution, and wavelength coverage than many planetary flybys or orbiter missions. The planet Mars itself will be a prime target for JWST. Millam said JWST would enable real-time observations of the entire Martian disk at wavelengths not accessible from ground-based observatories. In addition to the solar system, JWST will also study comets and asteroids. Instead of studying a single target, as with flybys and landers, JWST will study a sample of comets, providing a detailed analysis of a statistical sample. Our solar system has 4 giant planets: Saturn, Jupiter, Uranus, and Neptune. Uranus and Neptune have been the least explored among our solar system's planets, and the JWST is an ideal tool for future research. All the moons of our outer planets are outer planet satellites. Millam believes that JWST will enable us to observe geological activity on active bodies like Io and Enceladus, the ring system, and small satellites. Millam says JWST will not only identify ring systems across the solar system, but it will also detect new ones, possibly even around Pluto if they exist. Since the JWST cannot point towards the Sun, it will not observe Mercury or Venus. In any case, it will observe objects in our solar system beginning at Mars orbit and continuing outward. In addition, will JWST be able to make a variety of serendipitous observations? According to Millam, detection and characterization of plumes and other geological activity on natural satellites. According to Millam, observations can also be conducted as soon as 48 hours after a decision to observe a target is made. Essentially, the James Webb Telescope will be the most exciting thing to ever happen in space research and solve all the present mysteries we have.
Lana,